Okay, so keeping on with the aldol, I'm going to show you this time a simple aldol reaction. All right, recall that an aldol is an enolate reacting with a neutral electrophile that's an aldehyde or ketone. So in this case, in the simple aldol, I'm not sure how to say this. The reaction is between identical carbonyl molecules. Okay, so X here, it actually can't be anything. The X here, the aldol has to be whatever this is. So I'm going to show it for acetaldehyde. All right, then we can come over here, that gets rid of that. And it gets rid of that. There we go. I just blew too much away. Okay, so for example, let's do down here, let's take propionaldehyde. And we're just going to treat this with sodium hydroxide in water. And this can be catalytic. All right, for the aldol reaction, you can do this catalytically. So you have to make an enolate. How do you make an enolate? You have a base react with an alpha proton. We've only got one kind of alpha proton. The alpha proton's on this CH2. So hydroxide takes that. And now I'm going to draw the enolate this way. Again, you can draw your enolates however you like. You can draw them with a carbon-carbon double bond and a negative oxygen. You can draw them with a negative carbon and the carbon-oxygen double bond. You should be able to do both, okay? You might see both. I might ask you to draw both, but when you're given a choice, you can draw it however you like. I tend to like to draw them this way because it reminds you that the carbon is nucleophilic. So the enolate, we've now made an enolate, and it's going to react with a neutral aldehyde. So the neutral aldehyde is going to be propionaldehyde. So this carbon attacks there. And again, this is reversible. So there's our aldehyde product. You can draw that however you want. Maybe you want to draw it a different way. We can turn this thing around. We put the aldehyde there. Maybe that looks better. It doesn't really matter, and I'll work through it. You draw it however you want, and I'll trace everything around. Okay, and now this reaction is being run under aqueous condition in water. Okay, so now water provides the proton, and this gets us our addition product. And I dropped the carbon. Make sure you count your carbons. Don't drop carbons. And so this is two propionaldehydes coming together. So the simple aldol, now maybe this sentence makes sense. A simple aldol is going to be the enolate of a carbonyl compound reacting with a neutral version of itself. So propionaldehyde enolate reacting with propionaldehyde. Up here, acetaldehyde enolate reacting with acetaldehyde. Okay. And then, of course, under basic conditions, if we're heating this up, water can grab this proton. We make the enolate, and then that negative charge can kick out hydroxide. And so this is our condensation product. All right, so that's the simple aldol addition and condensation. So pause, take a look at it, go back through it. The next thing to ask yourself is this a reaction worth doing? It's a reaction where if you make an aldehyde like propionaldehyde, you got to be careful with it, right? If you make an aldehyde that's got an alpha proton and you leave it with some base or acid, then this reaction can happen. But what happens if you try to? This always just gives you a dimer, right? This is a dimer, which means 2, so 2 of propionaldehyde. Well, what if you don't want that? What if you want this? I want the propionaldehyde enolate to react. Next section. I want the propionaldehyde enolate to add into acetaldehyde. Okay, well, let's do that. So let's take our mixture, propionaldehyde and acetaldehyde, and dissolve sodium hydroxide in there. Well, yeah, you'll get this. So you will get, right? So sodium hydroxide can pull a proton off of propionaldehyde. The propionaldehyde enolate attacks the acetaldehyde. But you'll also get the one we got up above. Okay, so we'll make that. Hydroxide will come and deprotonate the propionaldehyde. And now you've got a lot of propionaldehyde and a lot of acetaldehyde. The propionaldehyde can attack either one of them. Okay, you'll also make, maybe get a different color once in a while. Hydroxide can take this proton just as easily as it can take this proton, right? And now the acetaldehyde can attack propionaldehyde. So we'll also get that compound, acetaldehyde enolate attacking propionaldehyde. And then acetaldehyde enolate can attack acetaldehyde. So we'll also get Aldol. So unfortunately, we'll get 4 different aldehydes. In reality says we get all 4. So you need to do a directed. Directed aldols are covered in the next video. Okay, there's an or to this. So you need to do a directed aldol, or, I'm gonna have to cover this up. Benzaldehyde, acetone, aqueous hydroxide. And now, we can only get one addition product, okay? Enolizable. So benzaldehyde, if we react benzaldehyde and acetone, you can't deprotonate benzaldehyde. The alpha position has no hydrogens on it. Right? No hydrogens on the alpha position. So the only enolate we can make is on acetone. And now acetone can choose to attack either benzaldehyde or acetone, right? There's plenty, this is a reversible process. The whole point here, which I conveniently haven't said, right? Hydroxide making the enolate is reversible. So right? This is reversible, and in fact, the left side of the equation is favored. The only way to get this to go to completion is because the enolate reacts and gets that Le Chatelier's principle pulls you along to the product. Okay, so there's plenty of neutral acetone around that the acetone enolate might attack. But acetone, or ketones have 2 electron donors on the carbon, so they're electronically a little less electrophilic, and these 2 methyls are sterically bigger. So this is an H here, and so this is fat. The enolate attacking the aldehyde is faster than attacking the ketone. I'll write that down. Enolates attack aldehydes faster than ketones. Okay, so we get this one product. Now, at this point, So we lose water here, either acid or base catalyzed, and we get a highly conjugated alkene. So this is, any time you have an alkene that would be, this, doing an elimination there, losing water, conjugates the benzene ring and the carbonyl, that's going to be a really easy elimination to do. Okay, that's it for simple and mixed aldols. And the point here, again, I should summarize, I should say this. All right, so the simple aldol is going to use a weak base, hydroxide, alkoxide, triethylamine, and you're never going to make a lot of enolate at a time. Okay, so that means that you're either going to have the enolate attack another neutral molecule of itself, and that's great if you need a really symmetric molecule, or you need to have an electrophile, you need to have one of the two components that cannot make an enolate. Benzaldehyde, think about things you could do that way. Pitylaldehyde, where you have a T-butyl group here. Anything that doesn't have an alpha proton can be an electrophile in the simple aldol reaction. All right. Directed aldol is next.